Hello students, in the last video we have discussed about introduction part of singularities, means the type of singularities, definition of singularity, and removable singularity, essential singularity, and pole. So now in this video let us discuss about theorems regarding this pole and singularities. So the first theorem is, if f of z has a pole at z equal to a, then mod of f of z tends to infinity as z tends to a. So here it is a pole, that z equal to a is a pole of the function f of z, then magnitude of that function tends to infinity as z tends to a. So means in case of finding the pole, we are equating the denominator to 0 and finding the value of that z. So if that z tends to the value of a, then the magnitude of the function will tend to infinity. So here let z is equal to a be a pole of order m. Let us consider that z equal to a as a pole of order m. Now by Lorentz expansion, so by using the Lorentz expansion, that f of z can be written as summation over n equal to 0 to infinity a n z minus a whole power n plus summation over n equal to 1 to infinity b n z minus a whole power minus n, or that is summation over n equal to 0 to infinity a n z minus a whole power n plus summation over n equal to 1 to infinity b n divided by z minus a whole power n f of z. So here it is given that z equal to a is a pole of order m. So by using the definition of pole, so pole means that analytic part, sorry, the principal part of the Lorentz expansion should have some finite number of terms. So here it is given that z equal to a is a pole of order m, means this principal part is having m terms. The order of a pole will give the number of terms in the principal part. So here we have m is the order, means the principal part has containing m number of terms. So therefore here f of z is equal to summation over n equal to infinity a n z minus a whole power m plus, now let us expand this one, b1 divided by z minus a plus b2 divided by z minus a whole square, and so on up to bm divided by z minus a whole power m, because it is containing m number of terms. Then this is equal to summation over n equal to 0 to infinity a n z minus a whole power n plus, let us take that z minus a whole power m common, then remaining terms. So let us write the remaining terms, that b1 z minus a whole power m minus 1 plus b2 z minus a whole power m minus 2, and so on up to bm. So by taking that 1 by z minus a whole power m outside. This is the remaining expansion. Now here, as z tends to a, as z tends to a, this term tends to 0, and here in this expansion, this is 0, this is equal to 0, means whole term is equal to bm, right? And remaining thing is 1 divided by z minus a whole power m into this bm, and here 1 by z minus a tends to, here 1 by z minus a whole power m is there. So as z tends to a, that becomes 1 by 0. So it implies that the whole function tends to infinity. So now as z tends to a, the expansion or the expression on RHS tends to infinity, right? Because the first term is equal to 0, and this whole term will become bm, and the denominator becomes 0. So therefore bm divided by 0, it means that it tends to infinity. So therefore as z tends to a, mod f of z means magnitude of that function tends to infinity, which is the required proof of the theorem. The next theorem is, if an analytic function f of z has a pole of order m at z equal to a, then 1 by f of z has a 0 of order m at z equal to a, and conversely. So here, while equating 0 and pole, we are equating the denominator of the function to 0, and for finding the 0, we are equating the numerator of the function to 0. So therefore here, if f of z has a pole of order m at z equal to a, then reciprocal of that means the numerator becomes the denominator and denominator becomes the numerator. It means that the same z equal to a will become the 0 of the function, and conversely means if 1 by f of z has a pole of order m at z equal to a, then f of z has a 0 of order m. So therefore that f of z, the pole of the function will become 0 of 1 by f of z, and pole of 1 by f of z becomes 0 of the f of z. So here let z equal to be a pole of order m. So by Lorentz expansion, so here we know that f of z can be written as summation over n equal to 0 to infinity a n z minus a whole power n plus summation over 1 n equal to 1 to infinity bn divided by z minus a whole power n. Now since a is a pole of order m, so this is z minus a whole power n plus, now this becomes b1 upon z minus a, b2 upon z minus a whole square, and so on, bm upon z minus a whole power m. It means that principal part of the Lorentz expansion contains m number of terms. Then it is equal to summation over n equal to 0 to infinity a n z minus a whole power n plus here taking that z minus a whole power m common as in the previous case, then here remaining b1 z minus a whole power minus sorry m minus 1 plus b2 z minus a whole power m minus 2 and so on bm. Then now taking this 1 by z minus a whole power m common from these two terms, then 1 divided by z minus a whole power m remaining n equal to 0 to infinity a n z minus a whole power n divided by z minus a whole power m, because we have taken that 1 by z minus a whole power m, or here plus here it is outside, then remaining this one. Now this becomes minus m, because we have taken that z minus a whole power plus m outside, then remaining z minus a whole power minus m. And here this expression, let us write this as bm, then bm minus 1 z minus a whole power 1 and so on b2 z minus a whole power m minus 2 plus b1 z minus a whole power m minus 1. So this is equal to 1 divided by z minus a whole power m. This is summation over n equal to 0 to infinity, and this becomes an into z minus a whole power n plus m, taking this to numerator, plus this is bm and so on up to b1 z minus a whole power m minus 1, and consider this as equation number 1, that is f of z. Now taking this z minus a whole power m2, that LHS, now that is f of z into z minus a whole power m is equal to summation over n equal to 0 to infinity a n z minus a whole power m plus n plus bm plus and so on up to b1 z minus a whole power m minus 1. So instead of this, consider this as equation number 1. So here this is f of z z minus a whole power m equal to some function of z. So this whole equation is a function of z, and consider this as equation number 2. Now RHS is a function of z. So here phi of z is an analytic function and phi of a is not equal to 0, means at z equal to a the value of this function is not equal to 0. Then here 1 by f of z is equal to z minus a whole power m divided by phi of z. So it is by equation 2, f of z equal to that phi of z divided by z minus a whole power m, and 1 by phi of z will be z minus a whole power m phi of z, and consider this as equation number 3. Now let z tends to a in equation 3, and we know that phi of a is not equal to 0. So here let us apply the limit as z tends to a. If z tends to a, this becomes 0, the numerator, and this becomes phi of a, and we know that phi of a is not equal to 0. If phi of a is not equal to 0, then 1 by f of z becomes 0, because here numerator is 0 and denominator is a non-zero quantity. Then it implies that 1 by f of z tends to 0 as z tends to a. So here if the value of the function is tending to 0 for some value of z, then we can consider that value of z as a that value of z as a 0 of the function. So it means that here initially we have considered that z equal to a is a pole of order m for the function f of z, and now the same a, that z equal to a, becomes the 0 of the function 1 by f of z. So therefore 1 by f of z has a 0 of order m at z equal to a. Means here we are equating the numerator z minus a equal to 0 and its power is equal to m. So therefore that z equal to a will become the 0 of order m. Now let us prove the converse part. So conversely, let 1 by f of z has a 0 of order a, of order m. Now let us consider 1 by f of z has a 0 of order m, and we need to prove that f of z has a pole of order m at the same point. Now 1 by f of z is equal to z minus a whole power m into psi of z. So here in the equation 3 we have 1 by f of z equal to z minus a whole power m into 1 divided by phi of z, that 1 by phi of z is equal to psi of z, that is equal to 1 by f of z, where psi of z is an analytic function and psi of a is not equal to 0. So this is our consideration. So therefore 1 by psi of z can be written as f of z into z minus a whole power m, because here we can write psi of z is equal to 1 divided by f of z into z minus a whole power m, that is psi of z, then reciprocal of that is equal to f of z into z minus a whole power m. And we know that 1 by psi of z equal to phi of z, f of z into z minus a whole power m. So therefore f of z equal to phi of z divided by z minus a whole power m. So here 1 by psi of z equal to phi of z, then f of z equal to phi of z divided by z minus a whole power m. So here we know that psi of z is analytic. If psi of z is analytic, then reciprocal of this, its reciprocal is phi of z is also analytic, and psi of a is not equal to 0. It implies that phi of a is also not equal to 0. Then it implies that as z tends to a. Now as z tends to a, this phi of a is a non-zero quantity, and the denominator becomes 0 at z equal to a. Means whenever we are finding the pole of the function, we are equating the denominator to 0, right? And here z minus a is equal to 0, then z equal to a, and the order of that term is m. So therefore z equal to a is a pole of order m. So therefore it implies that as z tends to a, f of z tends to infinity. So it implies that f of z has a pole of order m at z equal to a. So therefore 0 of the 1 by f of z will become the pole of the function f of z, and pole of f of z becomes 0 of 1 by f of z. So this is the required proof, and this theorem is very important.